Hello guys, welcome to another problem solving with special session with Special Maths Academy. My name is Ogene Obukume Jaffe, and today we'll be looking at problem 1 from the first physical international contest post-pandemic era, that is EGMO 2022. This contest is actually very special to us at SME, particularly this year's edition, because for the first time, SME was featured on an international platform. Yes, we had one of our members there, particularly our founder, Dr. Wahab. He was there, I think, as a keynote speaker. So it's actually very special to us at SME. Yeah, so yes, and it's also the first international contest post-pandemic. So this means that if we could host this physically, then it means that a physical IMO with the traveling and the interaction and all is possible later this year. For your info, the IMO will be held in Norway around some period in the middle of July. So with that, let's look at this problem. Today, the problem 1 is a geometry problem, and it goes like this. Let ABC be an acute angled triangle in which BC is less than AB and BC is less than CA. Let point P lie on segment AB and point Q lie on segment AC, where P is not equals to B, Q is not equals to C, and BQ is equals to BC is equals to CP. Let T be the circumcenter of triangle APQ, H the orthocenter of ABC, and S the point of intersection of the lines BQ and CP. Prove that T, H, and S are collinear. Okay, so that's our problem. So I'll go to a new page now because I already drew the diagram for this problem in a separate place. So you can see the diagram. You already constructed this on GeoGebra. So we have points A, B, C, and all that. So we have to prove that T, S, and H are collinear. So before doing that, let's understand what these points are. What points T, S, and H actually mean. So we have that H is the orthocenter of ABC. Then we have that T is the circumcenter of ASAPQ, and we have that S is CP intersection BQ. I want to prove that H, C, and S are collinear. Okay, so this is what we want to prove. Okay, we also have that BC is equals to BQ is equals to CP. They are all equal in length. So this is, we want to prove this with all these conditions. Okay, so for this problem, we'll be using a phantom points approach for this. What do I mean? Let's look into that. Okay, H is the orthocenter. The orthocenter is actually the concurrency point of the three median, the three altitudes. That's what H is. So ideally, so by this definition of H, that means H lies on the perpendicular from B to AC. That's what this means. H has to lie on this line. H lies on the perpendicular from B to AC. But you keep this in mind as we go on. So if you look from our diagram, I already drew the perpendicular from B to AC. I already drew it. You can see it that the perpendicular from B to AC, meets AC at B to AC meets AC at D. You can see that on our diagram. I already drew that here, so you can see point D. This is point D. Okay, so assuming this problem was true, if this problem was true, assuming, then it follows that TS intersection this perpendicular intersection BD, in this case BD perpendicular must be equal to H, because two lines can intersect at most one point, and if assuming H, S and T were actually collinear, then that means TS has to meet the perpendicular at that point H. So we'll use a phantom pointer point. I'll say let TS intersection BD be equals to K. We'll prove that K is the orthocenter of ABC, or rather K equals to H. That's what we're going to prove. How do we do this? We know that if K equals to H, then CH, if K is equals to H, let's see, if K is equals to H, if K is the orthocenter, then we know that CK has to be perpendicular to AB. You can check this. That's what it means. Yes, CK has to be perpendicular to AB if H was the orthocenter. So that means, and I've already said that from the diagram you can see, let's go. From the diagram you can see that CK, I've already called CK intersection AB. Okay, I've called CK intersection ABF. So I'll prove that angle CFA is 90 degrees. Once I do this, it means I will have an altitude. So that's what I will be doing now. So to ease of access, I might want to bring this diagram down a little, because so I need a sketch of the diagram. So I'll just draw a smaller one there. I'll draw a smaller diagram here. Let's see something like this. Okay, let's go down. It's too small here, because we want to solve downwards. Okay, so this is the triangle, not too accurate, just something we can work with. So this is point D, this is point B, this is Q, this is A, P, this is point, this is S, B into C, Q is S, this is point C, this is point K, and I want to show that CK, I said CK met this at point F, this is D, so I want to prove that angle CFA is 90 degrees. That's what I want to prove. So ideally, okay, this is APQ, second circle somewhere around here. This is just a sketch of that. So I want to prove this. So first of all, this is all geometric problems. The first major step is to have a chase. So we know that, let me clean this. This is T. Okay, this is T. Okay, so this is A. So since this is the circumcenter, since T is the circumcenter, we know that angle PTQ has to be equals to 2A. Angle at center equals 2 times angle at circumference. At circumference theorem. Maybe this is basic circle geometry. So this is something like 2a, and we know that TQ and TP are equals to the radius of the circle. So this should be 90 minus a. I think I might want to clean this triangle. It's literally a bit too small for this purpose. Let's make it a little bigger. We have all the space. There's no need to minimizing and drawing clearer diagrams. Just give me one. After all, if you always want to page, you always put in that slide. That's most case scenario. Call this D. This was P. This was Q. This was F. Okay, this was, sorry, this should be, this was D, this was Q, yes, this was P, A, P, Q, this was the second center, T, I think this was like TH, okay, let's put T somewhere around here. Draw this, this was point J, and we're trying to prove that this was F, this is K. We're trying to prove that angle CF is 90 degrees, so we're trying to show that this is 90, that is the thing. So we already said this was A, then we knew this was 2A, then I'm going to change to another column now. This is 90 minus A, 90 minus A. Okay, then what else do we know? We also know that this entire angle here is, since BC is equals to BP, then angle BPC is equals to angle BCP, which is equals to C. So I'm going to write that out here. So this is also C. This is C. This is 90 minus C. 90 minus C. Okay, so far so good. Okay, forgot to label S. This is point S. Then we also know that since BC is equals to BQ, then angle CBP is equals to angle BQC, and this is equals to B, because angle CBQ, sorry, angle CBQ, based angles of an isosceles triangle is equals to BQC. So this is also B. So this is B as well. This is B. This entire angle here is B. Okay, so we know this. This is now, let me use blue marker. So this is something like 180 minus 2B. So when we use this information, so from then we can continue our angle chasing now. Then you can say from triangle BCS, angle BSC is 180 minus 2C. That's for this entire angle here, plus 180 minus 2B. If you do this correctly, you should have something like 2C plus 2B minus 180. And if we recall, we know that A plus B plus C is 180 from triangle ABC, and that means B plus C is equals to 180 minus A. So this is 2 into 180 minus A minus 180. This is 360 minus 2A minus 180. This is 180 minus A. Triangle BSC is 180 minus A. You know that angle BSC is equals to angle QSP. The reason is vertically opposite angles. Let me write it out. Vertically opposite angles. So this angle QSP, and this is equals to 180 minus. So okay, this is 180 minus 2A. Sorry, 180 minus 2A. Okay, so I'll write it here. So okay, let me use this is 180 minus 2A. So that is 180 minus 2A. So another thing you might want to look at now, if you consider, let me go back to black. If you consider triangle, quadrilateral QSPT. Let me use QSPT. You can see QSPT. You observe that angle QSP plus angle QTP is equals to 180 minus 2A plus 2A. That's equals to 180 degrees. What does that mean? That means QSTP, and then this means that QSPT is a cyclic quadrilateral. Nice, right? This is a cyclic quadrilateral, so it means there's a circle somewhere around here. I'm drawing the circle in pink. There's a circle. Okay, so that's a nice observation. How do we use that? So this means that that means angle QST is equals to angle QPT, and that's equals to 90 minus A. Let me show you here. I'll use A. These angles are equal, and the angles in the same colors are equal. They are also equal, and that means angle PST is equals to angle TSQ also equals to 90 minus A. These equalities are avoided because of equal angles in the cyclic quadrilateral. So 90 minus A, 90 minus A, and that means that means that this line TS, that means line TS bisects this angle here. Line TS bisects angle QSP. Since these two are equal to 90 minus A, 90 minus A, 90 minus A stuff, so this is bisecting. And this bisection also means that line TS also bisects angle QSC, okay, angle BSC from this bigger triangle up here from this. TS also bisects angle BSC. So this angle here is also 90 minus A, 90 minus A. But if you notice, we're actually done. Why? Because let me just go through that slide for you to Let me come downwards and draw a diagram again so you can see why. So we can write out everything we have so far. We're actually done. Just relax and see why. This part is actually the interesting part where we get to close the problem. The eureka moment. This is Q. We had S. This was S. This was K. This was T. And let's write out what we had so far. Okay, so far we have proven that. Okay, let me write it out. We showed this is A plus C B. We showed that TS. Okay, sorry, TQSP is cyclic. We've shown this. Then we also showed that TS bisects angle QSP. And not just that, we also know what is bisected into 90 minus A ratios. So we had something like here as 90 minus A, here as 90 minus A, and this was 90 minus A as well, and 90 minus A. Then initially from 90 minus A, from the problem we had here was 90 minus C, 90 minus C. Okay, so if you are observant from triangle BSC, you can see that, okay, this was D, I forgot, then this was F. From triangle BSC, you see that line TS, I see as line KS. Line KS bisects angle BSC. And you can see that line BD bisects angle CBS. So we see that K is the concurrency point of the two bisectors. So what does this mean? It means that K is actually the incenter of triangle BSC. Why is this important? Okay, if this is K is the incenter, then we have that CK bisects angle BCS. CK has to bisect this. That's what I mean. So this and this have to be equal. But we know that this is 180, but we know that angle from our initial calculations, our angle BCQ is equals to 180 minus 2b. We already had it before. So angle BCK, which is will be equals to angle KCS, which is 180 minus 2b all over 2, 90 minus b. So this is 90 minus b, 90 minus b. Then that means then angle BFC will be 180 minus angle CBF plus angle BCF. And angle CBF is B. You can see angle CBF is this entire angle here. This entire angle in green, and that is equals to B. And angle BCF is 90 minus B. So this is 90 degrees basically. So this angle is 90 degrees. But initially, this was what we wanted to prove. So if this angle is 90 and this angle is 90, that means K is actually the orthocenter. That means K equals H. Since why is K equals H? Since K equals H. Why? Since BF and CD and alt are altitudes, and K is equals to BD intersection. Okay, this is BD CF and K is BD intersection CF. So K is actually altitude. So K is equals to H. So that means T, S, and H are actually collinear. And we are done. That's all. I like this part. It's actually the closing part, the interesting part where we solve the problem. My favorite part. Okay, so guys, that's all for this problem solving session with Special Maths Academy. Interact with us on our social media handles: Facebook, Twitter, Instagram, YouTube. Solve our problem of the month, stand the chance of the future, and I'm sure by the time you get this, our podcast for this year is actually very special for us at SMA. We celebrated 3 years anniversary this year at SMA, so we had a podcast, and we also have a surprise for you. Well, I won't be disclosing that surprise until the podcast is officially out, so just stay tuned and keep practicing maths. Keep visiting this channel. As the IMO draws closer, we'll be posting more solution videos and more problem solving sessions. So bye.